Okay, perfect.
Yeah, so sorry about that. So anyways, when we did our measurement, we could actually decrease the uncertainty from the previous best optical measurement of that hyperfine splitting by about a factor of 8. And again, since I guess going back, maybe we can't go back. But anyways,
You have to click in with your, yeah, just click on it once and then it'll work.
Oh, I see.
yeah, so basically, that produces sort of a new limit on this alpha double prime. Okay. So the real thing that we're interested in, and it's been the subject of a lot of interest recently, has been the Rydberg constant. So here, what we'll kind of take the attitude of is that proton radius is known from muonic hydrogen, in which case, anytime that you make any other measurement of hydrogen, assuming that these QED corrections are known, we can basically extract a Rydberg constant from any one single measurement. Now, of course, if you're following this discussion from previous years, it's been called the proton radius puzzle. From that perspective, you would say, no, let's just use hydrogen alone and try to determine both the Rydberg constant and the proton charge radius. But I think that now people aren't really doubting that the muonic hydrogen radius is correct. And so maybe it makes more sense to instead just focus on saying that we'll assume that that's known from that measurement, and then we'll just focus on extraction of the Rydberg constant. So we decided to make a measurement of the 2s 8d5/2. And part of the reason why is because they'll show later that was one of the measurements that had some of the biggest uncertainty or the biggest discrepancy in the Rydberg constant determinations previously. And our measurement is pretty simple. We just take our beam of hydrogen and we send it through, and we first optically excite from the 1s to the 2s with a 2-photon transition in a beam. And then that now excited beam of hydrogen goes to another region where we do a 2-photon transition to drive the 2s to the 8d. If that transition is successful, we decay to the 2p and then back down to the 1s. And then it's really easy for us to detect this remaining 2s state. We just send it into a channel front electron multiplier. And so from that, basically, if the transition is successful, we basically see a depletion in this 2s state. That means that the measurements that we make, we get diffs in the metastable population when we actually manage to hit the transition. And the biggest problem is that to drive that 2-photon transition successfully, we have a large AC star shift. So while the measurement is, for the most part, pretty clean, I would say that almost all the statistics and all of the effort goes into characterizing this AC star shift. So we basically vary the power of the spectroscopy beam and then do an extrapolation as we go into lower and lower power. The measurement uncertainty gets larger, and then we're looking for, what's the transition frequency at 0 laser power. Okay, so like I said, this is basically the proton radius puzzle on one slide, but looked at from another perspective, right? Which is basically to say that the proton radius is known, and then these are all of the other measurements. And basically these black measurements here are done at Munich, and then these blue measurements here are done at Paris. And so when we did our measurements, we got something that didn't really provide much clarity. So this is where it came in. So we were disagreeing with both the old Paris measurement, but also the muonic hydrogen result. Or actually, I guess what you could say, so in this perspective, what's setting 0 is really the 1s 2s. So that's known really precisely. So basically, that's where we would expect the true Rydberg constant lies. I mean, CODATA would have the same opinion, right? And so we think that, there must be some unknown there in our measurement that we really have been puzzling over for the last couple of years. Now, one thing that's interesting is that, as I was sort of saying, if you look at Rydberg constant extractions, you do see that there seems to be sort of a trend. As we go up to higher in, we see a variation in the Rydberg constant that we extract. So you might be tempted to say that, could this be some indication of some new physics? And the answer is probably not, right? Because I think first of all, the discrepancy of the same transition measured in different places seems to speak against that. And then another thing is that very recently, there was a measurement at ETH actually, which went to very high end, went to 20 and 24. And actually, it's not included on the plot because it would be actually back in this region with air bars that would barely show up onto the plot. Yeah, so this is kind of where the current status is. So, you know, like I said, it's been a puzzle for us for the last couple of years. And this is kind of what we're trying to make some inroads on now going forward. So actually this 2S8D 5/2 measurement, initially what we were really hoping to do was to measure the 2S8S transition. And the reason why is that, you know, there's really only the one very narrow transition in hydrogen, which is the 1S2S. All other transitions are pretty broad, and we always sort of wring our hands about this. I did when I was a postdoc at NPQ. We just said, you know, why do we have to always be splitting these broad lines? And so the 2S8D 5/2 is actually comparatively fairly narrow compared to the other transitions that have been measured. But if you look at all those discrepancies, you would say, what would it take for you to get sort of on one side of that plot versus the other? It's basically the shift between the solid line and the solid line. So we're really, you know, it's a very a small shift that statistically you would say we should be able to measure, but it makes you a little uncomfortable. On the other hand, with the 2S8S, we have a natural line width of 144 kilohertz. And, you know, even better would be is if we could get a natural line width down to 50 kilohertz, where we really see a much more pronounced effect, you know, to do the measurements that we want to sort of resolve this puzzle. So there was a problem when we tried to measure this, which maybe we didn't fully appreciate, but in retrospect, it was obvious, which is that, you know, when we make our metastable beam, so basically this is sort of our hydrogen beam coming through here, gets excited to the 2S state and then crosses this second beam, which excites the 2S to the 8S. What it basically sees is as it crosses this Gaussian beam, it sees a fast fluctuating AC star shift. And so when that happens, if you go to a very narrow line with, well, that's another way of saying the atomic coherence is long. And so the atomic coherence is actually long enough to basically see that vastly varying AC star shift as it goes across the spectroscopy beam. And so what we would see is actually not a very narrow line, but also a very distorted line as it crossed. And like I said, this basically just has to do with if you integrate the optical block equations over this, you know, vastly fluctuating line shape. So we decided not to make a measurement of this transition, felt like it wasn't because we want to measure Lorentzian lines, right? So, but it did give us an idea, which is that perhaps, you know, just a simple technical fix for this is to do an AC star shift of the cancellation of our first beam. So basically just to introduce a secondary laser field, which just removes that AC star shift. So luckily, hydrogen is simple enough that even I can do the calculations. And so this is basically the AC star shift as a function of wavelength in hydrogen. And for the 2S12S transition. And you sort of see that, of course, there's regions as you get close, in this case, the 2S3P resonance, which is basically right here, that there is a region of negative AC star shift. And so, and this is where our spectroscopy beam sits. And so it's, you know, you can easily pick a place where that AC star shift is equal and opposite. And when we put this into our apparatus, we basically see that, okay, this is what the transition would look like, severely distorted. But then with this AC star shift cancellation, we can get a very narrow transition, which also has a much increased amplitude just because we don't have the transition moving as we're trying to measure it. So in a sense, this is maybe you would say a very kind of technical approach. But like I said, I think at least for myself, where we were always sort of wishing that we had narrower lines to measure, we were really excited to see this. And it produces a big increase actually in the statistics that we can get. And it just makes it, you know, much easier to determine these line centers with the narrower line. Okay, so I mean, in practice, you know, what does this involve? It just basically, we just need an ECDL at 652 nanometers. that we couple into the same optical cavity in our apparatus before we do the spectroscopy. So there's actually nothing that stopped us then from pushing this to higher transitions. So, basically all the transitions from 2S, 8S to 2S, 16S, all lie comfortably within what a tunable high SAP is able to probe. And so using the same, and all these different transitions also have the same negative AC starship coefficient around 650 nanometers. Which just means that then we could get narrow transitions here for basically all of these states, all up to 16S. There's a little bit of a variation in the amplitude, and that's just because the AC or the power in the cavity due to the reflectivity of the mirror sort of changes as we shift these different wavelengths. But what we've been able to get basically is Q factors on these transitions, which are about an order of magnitude better than anything that's been seen before. Okay. And maybe just one more point, which is that the other thing that we like about this is that if we're looking for physics where the Rydberg constant might vary as we change the spatial extent of the wave function, so more or less, really probing that Yukawa potential, it's nice to have one apparatus where this can vary, dramatically. So usually when I give this talk, well, maybe really quickly, I'll just, what are some of the improvements that we have with this? Well, first of all, like I said, so narrow resonances, better signal to noise. The other thing that's maybe one thing that I don't know if it could be a problem or not, but when we measure this 2S8D5 halves, there's an overlapping hyperfine structure between the f=2 and the f=3 that can't be resolved. Always made us a little bit nervous, I would say, but there's no obvious problem with that. I mean, it could be taken into account easily in the theory. But at least when we're measuring the 2S to NS, there is resolved hyperfine structure. There's no linear start shift, so that's the other problem too. So there's an overlap in the 2D5 or the 8D5 halves and 8F5 halves are exactly degenerate. So that produces a linear start shift, which we have to take into account, which is gone. And then it should be pretty suppressed Zeeman shifts. And just because there's very close G factors between 2S and NS and hydrogen. And then, the other thing that we're going to do going forward here is just an active cancellation. So this is just our electrodes. We need to have, quite a few electrodes. Our spectroscopy actually happens over a fairly large region. Just means that we really want to cancel the BC start shift carefully over lots of individual regions through the spectroscopy. And typically when I've given this talk to people that know about precision measurement, they think it's a terrible idea, right? And one of the reasons why is they say, well, you used to have one systematic effect, and now you purposefully introduced the second one, right? So now we have to characterize the AC start shift of both of these beams individually, and they say there must be a huge penalty for this. And I would say that, fair point, but the question is, how do you vary the power of these two beams? If you really cared about really understanding the AC start shift of both the 652 and the spectroscopy laser power exactly, then you would probably, widely sample a huge region of space, right? But we really don't care about that. We really only care about what the difference in the AC start shift between those two is. So you can kind of imagine if we concentrate our data points along the line, right? What we really care about is where the value is, where both of those are zero. And of course, we can't go to zero spectroscopy laser power, but we can sort of, point in the direction of the origin. And it turns out that if we do that, we think that there's no real statistical penalty for having these sort of two AC start shifts versus one. So maybe one more point. So thinking a little bit about Pete's talk. One other thing that's of course interesting is that you could also imagine hydrogen and deuterium, right? You can repeat all of these same measurements. So it basically just involves, of course, just adding one neutron, right, to the nucleus and seeing how things shift. And so I think that, I believe that there are these F constants that Pete mentioned in his talk, and so that's basically corresponding to these. But at least it makes sense, right, that if you can extract a Rydberg constant from hydrogen, And you can also extract the Rydberg constant from deuterium. Again, when you compare those, if you see some difference, it might be some indication of some increased interaction between the neutron and the electron. And in fact that, deuterium and hydrogen, that does set some nice limits, at least according to this paper, right, on this neutron electron interaction. And then there was recently another publication that came out in 2023, where they basically were saying, well, how far could this be pushed if we, for instance, continue to measure some of these higher transitions to extract better Rydberg constants in both hydrogen and deuterium? And, maybe to put it into some, well, basically, so the solid line here is saying if they measure the 2s, 20s in hydrogen deuterium to 100 hertz or to 15 hertz, these are potential bounds that could be set. Which is pretty daunting because, as we were sort of talking about earlier, to give some idea with this proton radius puzzle or this discrepancies in the Rydberg constants before, we really aren't figuring out where the measurements should be within 6 kilohertz or so. But I think that we'll figure that out. And then the next thing, if we actually want to push to this sort of precision, would really be that, at least for me, the challenge would be actually getting a frequency reference nearby, where you could actually, make these relative uncertainties of 10 to the minus 14 accurately. So far, we've been using sort of GPS as a reference. But in the future, it turns out that we recently hired 2 new faculty members in the department that are both ion trappers, and they're doing plot comparisons between ytterbium and calcium upstairs. And so when I saw their results coming in, I said, could we possibly send a fiber down to my lab? So I think that that's probably where we could go in the future to get higher precision. Okay, yeah, so thanks. I think that that's.
Okay, questions for Dylan?
Thank you. One question I kind of want to dig in on a little bit is actually on the anti-hydrogen.
Yeah.
Which I don't think the electricity.
Right.
And in particular, for the anti-hydrogen that we have on Earth, it's mostly in the relatively large kinetic field. Do you have a prospect for doing spectroscopy of hydrogen at that sort of
So I mean, so I have nothing that I'm doing, but I mean, I think that for a short time I was helping out on the ATRAP experiment, and at least then what we thought would be probably the best way to go is to basically just repeat these measurements like Dan Kleppner was doing, and to really have it in the same environment. If you could actually do spectroscopy on the hydrogen in the same environment as the anti-hydrogen, feels like that would be the best. But I certainly have no prospects of doing that anytime soon.
Dylan, thanks for the talk. For the cancellation of AC stock shift, do you have to worry about the two color? You have 2 different colors after all, and there's 2 fields of fluctuating with respect to each other's spatial.
Yeah.
And do you use cavity to accommodate both? Or?
Yes. Yeah. So both in the same exact cavity. And so actually one of the limitations. So if the line width here, for instance, is at least in part due. So there's some, we're not quite hitting the natural line width for a lot of these transitions. And at least part of it is that when we put it into the same cavity, the 2 beams have the same Q parameter, but that means that they have a little bit different weights. So it's impossible to cancel perfectly. Unless you did something really clever, but in some sense, I think that it would be better to have it not cancel perfectly, but be understood really well. Now, there's another possibility, which I don't know if it's, maybe it bothers some people and to other people not so much, but of course, you have these 2 standing waves, right? So really, as the atoms move through this, it actually doesn't see a perfectly canceled AC structure. It sees an AC structure which is fluctuating wildly, right? But it's averaged over pretty effectively. Yeah. So there shouldn't be anything that's really problematic about that.
Okay, Well, if there's no more questions for Dylan, I think we'll end the first session and thank all the speakers again. It's now lunchtime. We'll reconvene at 1:30 for the second session, and you're all on your own for lunch, but I encourage you all to have more discussion. Huh? Oh, there is lunch. Oh, I didn't even know. Okay. Amazing.
Hey, thanks. I was wondering